In this video, we are going to talk about infrared spectroscopy, which I will abbreviate it as IR spectroscopy. So we are going to look at infrared spectrum and how to identify functional groups present in your chemical species by looking at the infrared spectrum. We will also be doing a lot of practice questions, because for this topic in particular, practice is really important. If you don't do enough practice, then it's very difficult for you to answer the question correctly. So the theory behind it is not too complicated. If you have seen enough infrared spectrums, then you will be able to tell immediately which functional group is present. So before I begin, maybe I will just introduce the spectrum to you. So it is something that looks like this. Although it may look very complicated at the start, but if you know where to look at, you can easily identify the functional group present. So first, let's have a look of why this infrared spectrum works. So the infrared radiation, it's something that we feel as heat. And one very important fact is that organic molecules, it's usually colorless. So this means we can't use UV spectroscopy. So we can only use, because it doesn't absorb any color, we cannot use our the conventional UV spectroscopy that we have learned in year 11. So we need to use infrared spectroscopy. And this is because organic molecules, they absorb infrared light. Although they don't absorb colored light, it can absorb infrared light. So because of this, by looking at the wavelengths of infrared light absorbed, we can easily tell which functional group is present. So the way that we look at which wavelengths of light get absorbed is by looking at this infrared spectrum. So on the vertical axis, you can see it is denoted as transmittance. So this is really just the percentage of light, and this is infrared light, that get transmitted. It is either presented as 1 or 100%. So this means everything is transmitted. So this particular wavelength is not absorbed by this chemical compound. So everything have been passed through. And this is really rare. So in the real life, there's always some small loss. So the maximum transmittance is around 95%. So if you have something like this, which is around 0.9 or 0.95, then basically the light gets passed through this compound completely. So it is not absorbed. But conversely, transmittance rate of around 5% or even as low as 1% means nearly all of the energy associated with this wavelength is absorbed. By the compound. And this is really important because we can use this fact. So if we see something like this, where the transmittance rate is really low, we can use this fact to deduce which functional group is present. So which functional group is actually there to absorb this energy. And the way we can tell is to look at the wave number. And then we can match the wave number with what we have given on the data book. So this is the section 22 of your data book. And you can see that for each particular type of bond or functional group, you get some particular wave numbers. So this indicates that whenever you have, for example, the OH bond for alcohol, so the hydroxyl group present, you will literally get very low transmittance at around 3200 to 3600 wave number. So this is how you read information from the data book. So whenever you see a very big drop around the 3600 to 3200 mark, then you can immediately tell that the compound being analyzed contains the OH alcohol or the hydroxyl group. So the unit of horizontal axis is wave number. So maybe this is a little bit unfamiliar to you. So you know about frequency, you know about wavelengths. So what is wave number? So wave number is essentially the same thing as frequency. So it is the amount of wave per centimeter. So that's why the unit is centimeter to the power of -1. So if we read this area here, then we can tell that this particular functional group or this particular species will absorb wave that is between around 3500 wave number. So the wave that with 3500 waves per centimeter, which corresponds to a particular energy. So perhaps the next question that you might ask is what causes certain frequency be absorbed? So why does the OH for alcohol absorb at this particular wave number, but the CH bond absorb at a different wave number? So this can be explained by a simple theory. So bonds are like springs. So you have two atoms which is connected by a covalent bond because we are dealing with organic molecules. So in a covalent bond, there's certain energy. So there's energy associated with this bond. And this energy is represented or it's stored as vibration or rotational energy. So each covalent bond between atoms will vibrate at a certain frequency. And this vibration frequency is the bond energy. So how strong this bond is. So for example, the CC double bond they have a shorter wavelength. They have a shorter distance, and it is stronger than the CC's single bond. And thus the CC double bond will vibrate at a higher frequency. So it has a stronger energy. Also, if the atom here is very heavy, then this means that the bond will vibrate slowly. So it has a lower energy, because when you have something that is very heavy, it's very difficult for them to vibrate. So it will absorb energy, so absorb light with a lower wave number, so a lower frequency, which means lower energy. So if the energy of the infrared radiation matches the energy of the bond, then you will get something called resonance. Resonance will occur, and the energy of the infrared light will be absorbed. And if the energy doesn't match, then the infrared energy will pass straight through the molecule. So you will not get any absorbance. And thus you have a very high transmittance rate. And when the energy of the radiation matches the energy of the bond, then we have a very low transmittance, because all of this energy have been absorbed by the bond. So after this energy be absorbed, the bond will vibrate at a higher state. So it will vibrate at a higher energy state. So this is essentially the theory behind infrared radiation spectroscopy. And we have determined experimentally that for example, the CO double bond for ester will absorb waves at this particular wave number. And we can use this result from the experiment to therefore deduce which functional group or which type of bond is present in the compound that we are investigating. Precisely because that each covalent bond have different strengths, and thus it will absorb wavelengths it will absorb waves at different frequency. So in essence, each bond is unique, and thus it will absorb unique wavelengths of light. Okay, now having done the introduction of infrared spectroscopy, we can look at how to identify which compound or which functional group is present by looking at the infrared spectrum. So this really takes a lot of practice, and I recommend you to do a lot of practice questions to be familiar with this type of diagram. So now let's have a look. So we already can tell from this diagram that we have propanol. So it is alcohol. In fact, it is one propanol. So the compound looks like this. So let's look at the type of bond that is present in this compound. So we have the CH bond. We also have the CO bond. We also have the OH bond. And some of the bonds are useful in identifying the functional group, and some of the bond is really not very useful. So the CH bond is not useful because essentially every organic compound contains CH bond. So we really can't tell which substances or which compound is present by looking at the absorption spectrum of the CH bond. The CO bond maybe is useful. So we know that there are really a lot of types of CO bonds. We have CO bonds in esters, CO bond in alcohols, things like that. So it is really not very unique. The OH bond is the useful one in this case. So if you think about the types of functional group we have learned, only acids, so the carboxylic acids and alcohols contains this OH bond. And a very important or interesting thing is the spectrum for OH bond for alcohol is actually different to the spectrum produced by OH bond of the carboxylic acid. You can also see this from the databook. So the OH for acids, you can see it absorbs a very broad wave number, so from 2500 to 3500. Whereas for alcohols, it absorbs a very narrow range of wave number. It's only from 3200 to 3600. So you would expect the transmittance or the spectrum for the acid to look very broad, whereas for the alcohol, it's relatively narrow. So if you see this kind of really narrow range, then you can immediately tell it is the alcohol, the hydroxyl group. For the acid spectrum, you know it goes from 2500 to around 3500. So it will look something like this, which is really broad, very big. So from this discussion, we can know that this is due to the OH bond in alcohol. And what about this very large drop? This is, if you look at wave number, around 3000. So we go back to the data book. And this is actually due to the CH bond. So this is due to the CH bond. And you can also tell the amount of bond present by looking at the depth. So you can see that this transmittance or this drop is very sharp. So a very deep drop. And this indicates you have a lot of CH bond present in this molecule. And if we look at our drawing, this is very true. So we have really a large number of CH bond present. So when you have a lot of bond present, each of the CH bond wants to absorb this energy from this particular wavelength. And thus you get a very low transmittance, since all of the energy have been absorbed as you have so many different CH bond present in this molecule. So that's the two characteristic peaks that we can identify. For this region, we can see we have a very high transmittance rate of around 95%. So we know that the light basically passes straight through this molecule. So there's really not enough information here. And if you go towards this region, so anything below 1500 wave number, you can see something very complicated. and it's really difficult for you to identify which peak corresponds to which substance. So this complicated part is called the fingerprint region. So by the name fingerprint, it should tell you something. So it can tell you, I can think of two things. So if you look at the fingerprint on your finger, you know it's very complicated. But another useful characteristic is that the fingerprint is unique. So each person, they have different fingerprints. And this also applies to organic compounds. Each organic compounds have unique fingerprint region. And we can't really do this in the exam, but in real life, what happens is people, they just don't care about this region. So the region that in the exam we care about is not actually not important in real life. So in real life, what people do is that they compare the fingerprint region with data bank in computer. So in computer, we have stored all the possible organic compounds and their fingerprint region. And whenever you will obtain this infrared spectrum, you compare this spectrum, the fingerprint region of the spectrum, with what we have in the computer's data bank. And then the computer will tell you which substances it is. So it's really like a fingerprint of a person. You can use the fingerprint and then compare it with data stored in computer to tell which person you are. So this is the fingerprint region. For the purpose of the exam, it is really not useful. If we want to identify specifically which compound we have, we need to use another tool called NMR spectroscopy. So I will discuss this in the next video. So for example, if you have propan 1-ol, so something like this, versus propan 2-ol, something like this, these two compounds will produce almost exactly the same infrared spectrum. So if you only look at this region, it will look exactly the same. But they will have different fingerprint region, of course, but you don't have access to computer to figure out which spectrum belongs to which. So if you have this case, then you need to use a different technique called the NMR spectroscopy. You can, from the IR spectroscopy, you can only know that you have OH bond present. So you know it is an alcohol, but you really don't know the structure of this compound. So now let's move on to a different example. So this is the infrared spectrum for ethanoic acid. So perhaps let's draw the structural diagram of ethanoic acid. So let's look at what type of bond we have in this system. So we have the CH bond, we have the CC single bond, we have the carbon-oxygen double bond, as well as carbon-oxygen single bond, and the OH bond. So referring back to the data book, we can see that the CC bond is not there. So it is not in the data book. Because it's not in the data book, we really can't do anything about it. The CH bond we have already talked before is present in every molecule, so it is really not useful. But perhaps we can compare this with propanol. You can see that around 3000, propanol have a transmission rate of around 0.05, so around 5%. But for ethanoic acid, around 3000, you can see the transmittance rate is quite high, so maybe it's around 20%. So why is this the case? It's because the ethanoic acid, they really have a very small amount of CH single bonds compared to a propanol. So that's why you have a shallow trough for the CH bond. And then we look at the CO double bond. So the CO double bond occurs in the wave number of around 1600 to 1700, as you can see from the data book. Be careful that this corresponds to CO for acids, and by acids we mean carboxylic acids. And we can see this absorption from the infrared spectrum. So if you look at here, this trough corresponds to the CO double bond. So whenever you see a very big trough around 1600 and 1700 area, then you should immediately know that you have a CO double bond. Because if you look at other absorptions for the CO double bond, it's all around this 1600, 1700 mark. So somewhere between the 2000 and the 1500 axis. So this is a very useful peak. So this is useful. The CO single bond is not in the data book, so which means it's not useful for us. And the OH bond is the most useful one. If you look at the data book, the OH for acids have a very broad wave number, so it absorbs a broad spectrum of infrared radiation compared to alcohol. So you can see that the trough ends at around 3500 and starts at around 2500. And this is exactly the same as what we would expect when we have something like carboxylic acids. So by looking at this very broad trough alone, we know that we have carboxylic acid. We don't really need to consider the CO bond anymore. So the CO bond is here, I think, to help you to verify your choice. So we know that the carboxylic acid have this CO double bond. So when you have already identified that because this trough is very broad, you should have carboxylic acid. And this is further verified by the fact you have a trough at the CO bond absorption region. So it must be carboxylic acid. It can't be alcohol because alcohol does not have the CO double bond. So that's how you decipher the infrared spectrum. The next one we want to look at is the ester. So this is isoethanoate. So this is how you draw the ester. I think it's always easier to draw from the acid side. So this is isoethanoate. So when we look at the absorption spectrum for isoethanoate, something very interesting happens compared to the acid. So again, we have the CH bond, we have the CO double bond, CO single bond. And what you can see is that because we have a lot of CH bond in this molecule, the absorption for the CH bond is very steep compared to what we have for ethanoic acid. So the CH bond, although not particularly useful, but you can tell that you have a lot of CH bond present in this molecule. So really the only useful one is the CO double bond, because we don't have any information about the CO single bond. So from the absorption region here, which is around 1700, we can see a very deep absorption. And the transmittance is basically zero. So all the infrared light with this wave number around 1700 have been absorbed by this molecule. So you go back to the data book and you see that for whatever you have, the CO bond have some wave number of around 1700. So you know you have a CO bond. And since you really don't have anything else, you can conclude that this is ester. So some of you may ask, well, it's possible to have aldehyde or even ketone if you say that you only have a CO double bond. And this is true. So I think in fact you can't really tell that this is an ester if you don't have been provided with sufficient information. So if they say the molecular formula for this is C2H4O2, then you can conclude this is ester. Because for aldehyde and ketone, you don't have two oxygens. So if they have provided you with molecular formula or something equivalent, as we will see in one of the later questions, if they have provided you with information like this, the molecular masses for the molecule was 60 and 74. And in many cases, the only possible combination is the multiple of C2H4O2. So if you use the formulas for aldehyde or ketone, you can never obtain a molecular mass of 60 and 74. So that's how you identify whether you have ester, aldehyde, or ketone. It's really, they need to provide you with more information. But here, since we already know it is ester, we can safely conclude that this molecule is ester. So the last one I want to talk about is infrared spectrum associated with primary amine. So since we have already talked about this many times before, we don't get a very deep absorption around 1700, so we don't have CO bond. So no CO bond. For the fingerprint region, we cannot really say anything about it, so we just ignore this region. There is CH bond present, which we should expect from every organic molecule. And the interesting thing is this region. You can see that it is different from the absorption region of carboxylic acid and alcohol. So it's have this inverted W shape. And this W shape is the telltale sign that you have this NH bond. So whenever you see this W shape, you know you have the NH bond. If you look at the data book, the NH bond occurs at a wavelength of 3300 to 3500, which also matches with this W shape. So we can tell that it has NH bond, so it is amine. So why is this not amide? So we know that amide is CONH2. So when when we have a very deep trough around here, then we can conclude it is amide, because it has both the CO double bond and this NH single bond. But for this one, since we don't have any CO double bond, it is amine. So that's all you need to know about the infrared spectroscopy. The most important thing is to do practice questions. So let's have a look of the practice questions. So question 1. Use the spectrum to identify this compound. The molecular formula is C2H4O2. Really, if you have given something like this, you don't really need to look at the infrared spectrum. From this alone, you can know that it's ethanoic acid. Because ethanoic acid have the molecular formula C2H4O2. But maybe it's safe to check, because maybe we can have something like this. So this dialcohol also have the molecular formula C2H4O2. So maybe it is this molecule. But in 99% of the case, it should just be ethanoic acid. But let's have a look. Let's check. And by just looking at this alone, absorption between 3500 and 2500, this very broad absorption, you know it is acid. This is further verified by the fact you have this absorption at around 1700. So you know it contains the CO double bond. So it must be ethanoic acid. So this question shouldn't take you more than half a minute if it appears on the exam. So now let's have a look at second question. So you need to identify the functional group present. So you don't need to name the molecule. And you know this molecule contains oxygen. So immediately you should think something like this. Whether it's aldehyde or ketone. But you don't need to name, so this process may not be necessary, but you should be thinking of this in your head. Again, this characteristic big trough at around 1700, which means we have the CO double bond. So what is the name of this group? This is called carbonyl group. Don't write carboxyl group, because carboxyl group is for the acid. And the next question, which families of molecules? So it's ketone, aldehyde. So really you need to look at the question carefully. I ignored part B. So in the exam, if you ignore part B, you lose half the mark, even though you have already identified that it could be aldehyde or ketone. So question 5. It gives you two possible structure of the compound. So A is, if you can see, is acid, so carboxylic acid. And B is with the ester linkage, so it's ester. So in fact, we can name the acid, so propanoic acid. And this ester is isomethanoate. So from this infrared spectrum, we didn't see a broad absorption at this at the 3500 to 2500 region. So you know it is not acid. So it must be ester, since it have the CO double bond absorption. So the correct answer is B. Question 6. Identify the major peaks in this spectrum for a molecule that has only one carbon atom. So only have one carbon. And you see this very broad absorption. Also, the CO double bond. So you know it is acid. So you know it is carboxylic acid. Only one carbon atom. So it is just methanoic acid. The last question, question 7. Use the diagrams to answer the questions. Identify the bonds responsible for major peaks on each spectrum. So you can also call this peak or trough, doesn't matter. As long as you are making yourself clear. And also a thing I want to emphasize is that the wave number goes from large to small. So this is also something you need to get familiar to. So the major peaks, I think we already done enough practice. You can immediately see it's the OH for acid and the CO double bond also for acid. So you know that both compounds are carboxylic acids. And question B is the interesting one. So by examining the peaks, determine which spectrum has the most number of CH bonds. So how do we do question B? So as I have already discussed in the earlier part of this video, so if you have more CH bonds, you have more absorbance. Thus, you have less transmittance. So you have a deep trough. So which one has a deep trough? We know that, so if you just compare across, that you know that the diagram A has deep trough. So you know that spectrum A has most number of CH bond. And then for question C, determine the possible molecular formulas for these two substances. So it contains only carbon, hydrogen, oxygen, and we know it is carboxylic acid. So what is the general formula for carboxylic acid? Maybe let's have a look. So for methanoic acid, it is it is CH2O2. For ethanoic acid, it is C2H4O2. For propanoic acid, it's C3H6O2. Hopefully you can see the trend. So you always have 2 oxygen. And the number of hydrogen is double the number of carbon. So let's look at which type or which families of. So let's look at which carboxylic acid has molecular mass of 60. Then let's just do some calculation. Maybe we pick ethanoic acid. So 12 times 2, so this is the mass for carbon, plus 4, which is for hydrogen, plus 16 times 2, this is for oxygen. Let's have a look. 12 times 2 plus 4 plus 16 times 2. Oh, it is exactly 60. So you know that for spectrum B, it is ethanoic acid. Then let's look at which one has molecular mass of 74. it can't be methanoic acid. It must be bigger than ethanoic acid. So let's choose the next one, which is propanoic acid. 12 times 3, this is for carbon, plus 6 for hydrogen, plus 16 times 2 for oxygen. If you redo the calculation, you get 74. So for picture A, it is propanoic acid. So that's the answer to question 7. If you have done enough practice, shouldn't be too hard. Because as you can see, it's really repetitive. Once you have seen enough spectrums, you can do everything easily.